Part 7, Lecture Chapter 1, the last part of this chapter. Let's look into the dimensional analysis in solving problems. Dimensional analysis is a procedure to convert between units in solving chemistry problems. It is based on the relationship between different units that express the same physical quantity. So, to apply dimensional analysis here, we use the relationship given quantity multiplied to the conversion factor to obtain desired quantity. And unit cancel as follows: given unit multiply to the desired unit over given unit to obtain the desired unit. Meaning that given unit and given unit here can be slashed out to obtain the desired unit. In dimensional analysis, the units are carried out through the entire sequence of calculation. Remember, units are carried out through the entire sequence of calculation. Therefore, if the equation is set up correctly, then all units will cancel except the desired one. For example, by definition, 1 kg equal to 1000 gram exactly. This equivalence enables us to write a conversion factor as follows: 1000 grams divided to 1 kilogram. Because both the numerator and denominator express the same length, this fraction is equal to 1. Similarly, we can also write the conversion factor as 1 kilogram over 1000 grams, which is also equal to 1. So that's why conversion factor are useful for changing units. Thus, if we wish to convert a weight expressed in kilograms to gram, we multiply the weight by the appropriate conversion factor as follows. This is a measured unit, which is 2.2 kilogram, multiply to the conversion factor here. So we choose which one we want to choose. Alright, because we want to obtain the desired unit as grams, so we insert kilogram as denominator because we want to cancel out kilogram with these kilograms. So that's why you multiply this measured value to 1000 grams over 1 kg. So your final answer is 2.20 times 10 to the power of 3 grams. Because we have cancel out kilogram with this kilogram, so your final unit is grams. Note that we choose the conversion factor that cancels the unit kilogram and produce the desired unit, which is grams. And the answer is expressed in 3 significant figures because 2.20 kilogram, which is a measured unit, consists of 3 significant figures. However, we do not consider 1000 grams because 1000 grams here is a conversion factor and considered as an exact number. So let's say we look into the significant figures and unit conversion. Example here, how many moles are there if you have 2.90 liter of hydrogen gas H2? So the solution here is 2.9 liter multiplied to 1 mole over 22.4 liter. So this is the answer that is given in your calculator. So since 2.9 liter is a measured number, so we have to consider this value. We have to consider the significant figures of this value to write our final answer. Right? So we do not consider 1 mole because 1 mole is an exact number. Alright, that's why we only consider this value, its significant figures, to give the final answer. That's why this is the answer given in your calculator. However, the answer that must be given by you in the answer paper is 0.13 mole because it considers 2 significant figures. 0 is not counted as significant figures, remember, but 13 consists of 2 significant figures. And this is another more or less similar example you can see by yourself. Alright, you have to look into these problems. Which one is a measured number? whenever it consists of more than one measured number, then you have to consider which one has the lowest significant figures, because these problems involve a multiplication. That's why for such problem, the answer is 0.611 mole, because we consider 3 significant figures from 13.7 liter. Let's look whenever we want to convert between grams and mole. What is the mass in grams of 4.30 mole of aluminium? The atomic mass of aluminium is 26.98 gram per mole. So 1 mole of aluminium weighs 26.98 grams. Thus, this is how we solve this problem. 4.30 mole aluminium. See, our targeted or our desired unit in the end is grams, is it? Because the question is what is the mass in grams. That's why your desired unit is grams. Alright? That's why whenever you use the conversion factor here, the conversion factor here is 1 mole of aluminium equal to 26.93 gram. That's why you put 1 mole aluminium as denominator, because you want to cancel out this mole with this mole, is it? So only then you can obtain your final answer in grams. That's why you put it such way. Right, so if you look here, 1 mole is not considered because it is an exact number, and the molar mass also is not considered its significant figures. So we consider 4.30 mole because this is a measured value. Alright, so that's why your final answer must be in 3 significant figures, which is 116 gram of aluminium. Please never forget to insert the unit at the end of the calculation. And then if you look here, how many moles in 127.5 grams of sodium chloride? So the molar mass of sodium chloride is 58.44 gram per mole. This one can also be obtained from periodic table. So this is the conversion factor. So your targeted unit is mole, is it? Mole, right? So that's why you put grams as denominator, because you want to cancel out gram with gram here. So only then you can obtain your final answer as mole. So in this case, you consider 127.5 grams, which consists of 4 significant figures. 1 mole is not considered because it is an exact number. Molar mass is also not considered. So your final answer must be in 4 significant figures, which is 2.182 mole of sodium chloride. Let's say you want to convert between moles, atom and molecules. If you look into the example here, how many atoms are in 5.5 moles of sodium atoms? So the solution is like this. 5.5 mole multiply to 6.022 times 10 to the power of 23 atoms per mole, because this is the Avogadro number. 1 mole consists of 6.022 times 10 to the power of 23 atoms. You know about this, right? So we put here mole as denominator because our desired unit is atoms. Because the question here is atom, is it? So this is the answer that is given by calculator. However, we have to consider this 5.5 mole. We have to consider its significant figures because this is the measured number. Alright? So that's why your final answer will be 3.3 times 10 to the power of 24 atoms, because you consider 2 significant figures from the measured number, which is 5.5 mole. So let's look into this one. How many moles in 4.6 times 10 to the power of 24 sulfur atom? So our targeted or our desired unit is mole, is it? Mole. right? So this is the measured number 4.6 times 10 to the power of 24 atoms multiply to 1 mole over 6.022 times 10 to the power of 23 atoms. This is a conversion factor. Alright, so we put Avogadro number here as denominator because we want to cancel the atoms with atom here because we want to get the final answer in mole unit, is it? Right? So as usual, you have to consider this one as a measured number which consists of two significant figures. That's why your final answer is 7.6 mole. Alright, okay, so this is more. This is also the same thing as well. Just we want to check if a conversion factor is used to solve the above problem. It is also similar, meaning that 1 mole is not considered as measured number. Alright, so we only consider this one as measured number. That's why our final answer must consider two significant figures for this value. Alright, so this one, how many chlorine molecules in 0.63 moles of molecules? So this is how you can solve it, like I said before. So let's use this method. It is similar, just like this method, but this one I want to show that 1 mole becomes the denominator because we want to cancel mole with mole. So we obtain 3.7926 times 10 to the power of 23 molecules. This is the answer from calculator. Alright. However, your final answer must be 3.8 times 10 to the power of 23 molecules because we consider two significant figures of 0.63 mole. Now, let's look into quantitative analysis. The data that is obtained during experiment must be recorded properly according to the type of glassware. Here is a guide while recording data for some of the common glassware in laboratory. For example, burette. Make sure you read the burette to 2 decimal places and record 2 decimal places for all your readings. Please remember this one, yeah. The smallest the smallest gradation on a burette are 0.1 milliliter, but you can estimate the second decimal place based on where the bottom of the meniscus lies between 0.1. Okay, 0.1 marks on the burette. A higher level of accuracy is gained if you read a burette, for example, to 0.05 milliliter or 0.02 milliliter rather than just 0.1 milliliter. Consequently, the average titration will then be of greater accuracy too. Also, if your burette reading is 14.00 mil, do not abbreviate it to 14, as this decreases the accuracy of your reading. So I will continue a bit about the quantitative analysis on the next part of this lecture. Thank you.